Hello, good morning to everybody. Here we are for the fourth lecture in Mathematical Analysis 1. I recall you that we were talking about sequences, so-called real sequences that are nothing but infinite lists of numbers, of real numbers. Formally, a sequence is a function whose domain are the naturals, whose target set are the reals. This function can not be bijective. We discussed it in our question time on last Tuesday. So to every n, we associate something which is denoted usually traditionally by an. Okay? Then we introduce the notion of convergence sequences. Let me, before recall what is the problem. The problem is to describe the asymptotic, where asymptotic means n very large, behavior of the sequence. I also pointed out that the behavior in general can be extremely various, okay, and extremely chaotic, difficult to classify, difficult to characterize. But there are some behavior that are quite simple, and the first behavior was that of the convergent sequences. I recall you also the definition of convergent sequence. So a sequence AN is said to converge to the limit, I stress the word limit, L, which is a real number, if for every epsilon larger than 0, there exists an n bar, natural number, such that after n bar, which means whenever n is larger than n bar, then the distance between an and L is not larger nor equal to epsilon, is strictly less than epsilon, okay? This is the definition. We explained a lot of this definition. I recall you that in our representation of a sequence as a graph of a function, if this is L, and if this is the limit L, you have that for every stripe, however thin you consider around L, and this is exactly here L minus epsilon, here L plus epsilon, sooner or later the sequence will fall inside the stripe and will not escape from that. Okay? So here basically n bar corresponds to this point here, and when n is larger than n bar, the sequence lies inside the stripes. The strength of this definition is that epsilon is arbitrary for every epsilon larger than 0. This means that you can also ask for more precision by designing a stripe which is thinner, very thinner around L. Okay? So this is the meaning of this definition. And we also introduce a first exercise. A first type of exercise was the following. Prove that a given number is actually the limit of a given sequence. We performed some exercise like that in the last lecture, and the philosophy is just to apply the definition. So fix epsilon and then find n bar. This is the kind of exercise. Then the last exercise I introduced in the last lecture was the following. Consider this sequence an, which is 1 over n, if n is even, and 1 minus 1 over n if n is odd. Of course, n cannot be 0. And I also started to discuss on the lines, on the other representation of the sequences, what happens. So here we have 2 points, 0, 1. So here you have 1 minus 1, which is 0, and this is A1. Then A2 is 1/2. I put the even here and the odd. A3 is 2/3. A4 is 1/4. And then we have A5 here, A6 here, A7, and here A8. So you see the odds always go rightwards towards 1, and the evens go leftwards towards 0. So the question is, what is the limit? Is it 1? Is it 0? Apparently they have the same right to be the limit, because there is no structural reason to prefer the evens or the odds. And so the natural answer can be the following, can be that both numbers 0 and 1 are limit. But notice that if you go to the other representation, so this is 0, this is 1. The sequence approaches both 0 and 1, but when it approaches 0, it is here, is far from 1. And when it approaches 1, is far from 0. So it is not true that for every stripe around 0, however thin, sooner or later the sequence is trapped there, because alternatively for odd numbers the sequence will jump around 1, and for even around 0. Vice versa, it is not true that for every stripe, however thin, around 1, the sequence is trapped inside there. So it is not easy to find the limit. And here it seems that indeed there is no limit, because if we try to trap the sequence around 1, then there are even elements that are around 0 and vice versa. And this is exactly the message and then the theorem. So the first message: a sequence cannot approach to different limits. And then it becomes a theorem, which is the first theorem of on limits that we prove, which is called uniqueness of the limit. And the theorem says the limit of a convergent sequence is unique. This is the theorem. So let us go for the proof. This is a nice proof. So suppose that there are two limits, so that an tends to L. Tend to is a way to introduce a limit. If I say a sequence tends to L, it means that L is the limit of the sequence. And an tends to L prime. Okay? Now, let epsilon be L minus L prime divided by 2. Okay, since we suppose that L is different from L prime, epsilon is larger than 0, so we can apply the definition of limit. So, by the definition of convergent sequence or limit, and of limit, we have that there exists n1 bar natural such that whenever n is larger than n bar 1, we have that the distance between the sequence and the limit is less than epsilon. But since an tends to L prime, we have that there exists n bar 2 in n, such that for n larger than n bar 2, an minus L prime is less than epsilon. So this is relationship 1 with an minus L less than epsilon, and the other I call it the relationship 2. Now, I consider n bar to be the maximum of n bar 1 and n bar 2. Why? Because if n is larger than n bar, then n will be larger than n bar 1 and n larger than n bar 2. So because when I take n larger than n bar, it happens that both 1 and 2 hold. Okay? So 1 and 2, the two relationships I labeled, hold simultaneously. Then consider the distance between L and L prime. You can write it as L minus an plus an minus L prime. I just added and subtracted the same quantity, so it is perfectly legal what I did. Now consider the associative property of the sum, so you can consider these two terms which are linked by sum here. So by the first triangular inequality, you have this is less or equal L minus AN plus AN minus L prime. Okay? Since 1 and 2 hold simultaneously, we have that both AN minus L in absolute value and AN minus L prime in absolute value are less than epsilon. So here we have less than epsilon plus epsilon, which is equal to 2 epsilon, but 2 epsilon, by our choice of epsilon, is the absolute value of L minus L prime divided by 2. So this is equal to, 2 times absolute value of L minus L prime divided by 2. So this is L minus L prime. So consider all this relationship, and what you find here is that L minus L prime in absolute value is strictly less than itself, and this is absurd. So what has been denied is our starting hypothesis, so the fact that AN tends to L and AN tends to L prime for L different from L prime. Therefore, it must be L equal L prime. So the limit is unique. Okay? And again, the geometric interpretation of this proof, the pictorial interpretation of this proof, is extremely easy. Because here we have L, here we have L prime, and so what we considered here was epsilon equal to L minus L prime divided by 2. So and so you see that here it means that we are considering two neighborhood of L and L prime that do not intersect. So in order to have the limit as L, eventually after some n bar, the sequence must be trapped here. But in order to have as a limit L prime, the same sequence must be trapped here. These two neighborhoods have no intersection. There is this line here, but we are considering less, strictly less sign, not less or equal. So there is no intersection, okay? And this is the absurd. This is so the first theorem on limits. So you can be surprised by the use of this n bar 1, n bar 2, and that's to take maximum. Just think of it. Okay. So and then there is another theorem which is quite famous, which is the theorem of the permanence of sign. Permanence of sign in limits. And the formulation is very classical, says that we have a convergent sequence AN that tends to L, which is a real number, and consider the hypothesis that L is positive, strictly larger than 0. Then the whole sequence AN is eventually positive. What does it mean, eventually positive? It means that eventually means that there exists n bar in n such that whenever n larger than n bar, then an is larger than 0. And the proof is quite obvious also from a pictorial point of view. Let me first go pictorially. There exists this line here. Here you have 0. Here you have L, sequence is positive. Now you just consider epsilon equal to L, so a neighborhood like that of L. Eventually, by definition of limit, the sequence must fall into this interval, but this interval does not contain 0. This interval is completely positive. Okay? Eventually, the sequence must lie in a completely positive interval. Proof. Proof is not problematic at all. This time we will consider epsilon equal to L larger than 0. Choose. So let me write choose. It is possible to choose epsilon like that because epsilon has the only constraint to be a positive number. So this means that there exists m bar in n such that for every n larger than m bar, then an minus L less than epsilon. So the distance of an minus L less than epsilon equal to L. So this means that an must be between L minus epsilon and L plus epsilon, because the distance must be at most epsilon. So, and this means that this is 0 less than an less than 2L. So the important part of the proof is this one, an larger than 0. End of the proof. Very simple and really reflects the pictorial reasoning that we made at the beginning. Just a remark, since we proved that the permanence of sign in the case of the limit L is positive, of course there is a completely symmetric result for negative limits. I just write it here as a remark, saying that if L is negative, then an, the sequence that converges to L, is eventually negative. Okay, this is an aspect of the theorem of permanence of sign, but there is also the other aspect. The other aspect here, which is the true permanence of sign, the fact that the signs resist to the limit. So let me write here in a clearer way as a corollary. I recall you that a corollary is a sort of immediate consequence of a theorem. It is a theorem too, but it follows so directly from another theorem, so we don't dare to give it the name of theorem. We give it the name of corollary. So the corollary says that if an converges to L and AN is non-negative, then L is non-negative too. Okay? Proof is immediate, as I told you. For the proof, just suppose L to be negative, then by the theorem of permanence of sign, from some n bar on, so eventually AN should be negative. And this is absurd, because it contradicts the hypothesis. The hypothesis that AN non-negative. End of the proof. And so notice that here I started from a non-negative AN, I ended up with a non-negative limit. But be careful. Because if I consider the case of not only of a non-negative sequence, but of a strictly positive sequence, AN strictly larger than 0, AN has a limit, L, then L is not true that it is strictly larger than 0. What is true is that AN is larger or equal. You have that L is larger than or equal to 0, exactly like in the other case. So when you pass to the limit, positivity is in general not conserved. It just amounts to non-negativity of the limit. Because you can be positive but approach 0. As you already have the example. The example is the very famous AN equal to 1 over n, which is strictly positive, and AN tends to 0. Okay? So, when you perform the limit, you can lose the strict inequality and just go for equal, larger or equal. Okay, the first part is here. Let us go for the second